Okay, so now that we've talked about simple machines, what they do for us, let's go a little deeper into what they do for us. Okay, so what is work? Work is the quantity of energy transferred by a force when it's applied to a body and causes that body to move in the direction of the force. Talked about it before. Force times distance. Work equals force times distance. We measure work in joules. Force times distance, so we know the amount of work we've done because we can tell the amount of force we've applied and the distance that has been applied over. Work equals force times distance. Work is measured in joules. It is measured in joules. The force is measured in newtons, and then we have a distance, so it's a newton meter, and we call it the joule. How many newtons have been applied over what distance? That is a joule. So easily to do equations. Work equals force times distance. We got a force of 10 newtons, distance of 1 meter. 10 times 1 equals 10. So that's 10 joules. 200 newtons. Move a car 20 meters. 200 times 20. That's right, 4,000 joules. 4,000 joules. Very simple. All right, so what is power? If we talk about work, we talk about things being powerful. What is power? Well, power is the amount of work you do over a certain amount of time. It's the rate at which work is done, right? If the Roadrunner and the Coyote go the same distance, they do the same work, right? The Roadrunner clearly gets there faster, so time is lower, so the Roadrunner must have more power. Roadrunner has to have power, and we measure power in watts. Measure power in watts. Power equals work divided by time. W over T, right? So we do 60 joules of work in 10 seconds. 60 work divided by time 10 gives us 6 watts of power. All right, so we've talked about machines making our work easier. So we call this advantage that machines give us a mechanical advantage, right? It's the amount or the ratio of your output to your input. How much does your output increase, or how much does it decrease in some machines? Unfortunately, that's a trade-off we use sometimes, but it works for us in certain situations, right? So it's a ratio, and ratios obviously involve division. Mechanical advantage, it's your output divided by your input. So what you get out of it divided by what you put into it. That is the mechanical advantage that machine gives you. Okay, multiplying forces. So a machine that multiplies force, mechanical advantage is going to be greater than 1, right? Your output is going to be greater than your input. Very simple. So if you put in 3,200 newtons, or the amount of work done is 3,200 newtons, you only put in 1,600 because you used a ramp, then your mechanical advantage is output divided by input equals 2. So let's talk about inclined planes, right? Mechanical advantage of an inclined plane is equal to the length of the slope, that is the long end, divided by the height, right? Where you're actually going with your motion, right? So slope divided by height, very simple. 15 here divided by 3, it gives us a mechanical advantage of 5. That's pretty good. Pretty good. Okay, what about a screw, right? Okay, a screw is basically an inclined plane wrapped around a cylinder, so it's probably going to be similar, right? The mechanical advantage of a screw is calculated by dividing the circumference of the screw by the pitch. That's the distance between the threads, right? So that's essentially the distance between the threads here. And you're just dividing the circumference by the pitch, right? And pitch equals 1 divided by the number of turns per inch. So how many times do you have to turn that screw for it to go an inch? Very simple, very simple. All right, a wedge, yet another inclined plane, right? So how are we going to determine the mechanical advantage of a wedge? You divide the length of either slope, right? Because you have the slope here. There's 2 of them because it's a double inclined plane. And you divide it by the thickness, right? the large end. It's essentially very similar to the height of the inclined plane. Very simple. Slope divided by the thickness of that wedge, and that's going to give you your mechanical advantage. Okay, first class lever, right? The mechanical advantage of a lever is the ratio of the length of the lever on the applied force side, that's the effort side, right? And the sides are from the fulcrum on to the resistance side, or the side with the load on it. So you measure this, right? You divide it by this. Measure this, divide it by this. Very simple. Effort divided by resistance. Wheel and axle. Mechanical advantage of a wheel and axle is the ratio of the radius of the wheel to the radius of the axle. Very simple. Very simple. You have a radius of 5 here from the inside all the way to the outside, and then you have a radius of 1 here, the inside, the axle part. Very simple. 5 divided by 1, you have a mechanical advantage of 5. Very, very simple. We just have to remember how to do these. The calculations are not difficult. You just have to remember what we are measuring. Right? Right. Okay, a pulley system. Mechanical advantage of a movable pulley. If you recall, a stationary or a fixed pulley does not give us a mechanical advantage. It's only changing the direction of our force. But a movable pulley, that is equal to the number of ropes that support that pulley, right? Here we got 2 ropes. Obviously, that's going to give us a mechanical advantage of 2. Here we have 1, 2, 3 ropes, mechanical advantage of 3. Still 3 ropes, mechanical advantage of 3. 1, 2, 3, 4, mechanical advantage of 4. Very simple. Okay, so when we multiply distance, for a machine that multiplies a distance, the output is unfortunately going to be less than the input. So for a machine that is changing the distance that you apply your force, your mechanical advantage is going to be less than 1. Right? So if you exert an input force of 20 newtons and the machine produces an output force of 10 newtons, then the mechanical advantage, 10 divided by 20, or half, 0.5. Not the greatest, obviously, because then you only get out half of what you put in. That is not always good, but sometimes we need it to change the distance of our force. It is necessary in some cases, such as in a class 3 lever. Sometimes we have to change the distance of our force, such as here, our fishing pole, right? We apply a force in the center here. We are pivoting with our other hand wherever we're holding the end of the fishing pole, and our load is right here. So clearly the amount of distance of our force here, very small, and then we apply it over a much larger distance. So it is not as easy, but fortunately we're generally not lifting very heavy things. Fish, not all that heavy. And so we don't need as much force, but we do need that greater leverage, that greater distance of our force. One would imagine that our muscles would be more efficient than they are, but another third-class lever here, our force is applied at a much shorter distance, so we are losing some mechanical advantage, but it helps us once again to have more leverage in order to lift that heavy weight. Alright, so sometimes you change the direction, and that is going to give you a mechanical advantage of 1. You're only changing the direction, not the amount of force, not the distance, but the direction. Here we change the direction of our force. We use the pulley. Instead of having to lift this straight up, we get to pull back this way, allowing us to use more of our energy in a more efficient, in a better way, but not multiplying our force at all. So a fixed pulley, as was stated before, only a mechanical advantage of 1, but it is still an advantage the machine gives us because we can apply our force in a different direction. Here we go, fixed pulley, same thing. Does not create mechanical advantage, only allows us to change the direction of our force, right? I want this box to go up. But I don't want to climb up here and pull it up. No, I want to be able to pull down on the pulley and pull up on the box, just like flagpoles, raising the sails on a boat. All those things are necessary. So, we know about the mechanical advantage of a machine. It is, right? Input can be equal to output, input can be greater than output, and unfortunately, input can be less than output. But we're never going to have a machine that works perfectly because of our old friend friction, right? The friction, enemy of all motion. So we're going to unfortunately waste some of our work in every machine. Going to go to friction. Friction probably going to turn into some heat, right? But the less friction, the better we are, the more efficient our machine is. That's why, once again, we lubricate machines. That's why we try to eliminate friction as much as possible to make things more efficient. When we talk about the efficiency of machines, we're talking about the output divided by the input, and we turn that into a percentage, right? So we know output by input, that's just what? That's mechanical advantage. We multiply our mechanical advantage by a percentage, and that tells us how efficient our machine is out of 100%. Very good, very good. Right? Once again, it's a percentage. The higher the percent, the more efficient our machine. It's telling us, what percentage of work we're holding on to. Right? So a machine that has an efficiency of 95% obviously loses very little work. Unfortunately, something that has 60% efficiency, we're losing a lot of work to friction. When you have lots of parts that are connected to each other, you're going to lose more of that work, right? Absolutely. Once again, that idea machine is going to have an efficiency of 100%. Not going to happen here on Earth, is it? No, no, no. Don't forget the formula for efficiency. Output divided by input. And multiply that by your percentage, your 100%, and gives you that percentage. So, I'm using a hand lawnmower, which I do not suggest, lots of work. 200,000 joules of work to move the mower. That's a lot. The work is 250,000 joules, so that's nice. Our efficiency being only 80%. That's why I would use a gas-powered mower. I put in much less work. So mechanical advantage of a machine in a real situation is the actual mechanical advantage. We can't really determine the actual mechanical advantage unless we actually measure those forces, right? Because we can do theoretical, we can think of it, oh, this is what it should be, but we actually have to measure the forces to find out the actual mechanical advantage, right? You don't know about it in advance because every situation is different. Friction is not the exact same thing in every situation, so you have to actually measure the input and output forces to determine mechanical advantage. Idea mechanical advantage, right? Without friction, mechanical advantage, efficiency, that idea situation always going to be thwarted by friction, right? We can lubricate our machines, oils and greases, those sorts of things make things, they cut down on that friction. However, it's never going to be perfect unless we're in a completely frictionless environment, such as, that's right, outer space. Our International Space Station moves in orbit around the Earth in a frictionless environment. Perfectly idea situation. Perfectly ideal. An ideal situation. That is all about mechanical advantage and mechanical efficiency of our simple machines.